Okay? That's my key goal for today. So, for some of you, I will already present the story. But you know, maybe from the second presentation, you will understand a little bit more. That's my goal, okay? So that is why what I'm planning to do today is to explain a very classical story. Practically all of you read in the classical book by Professor Khalil, okay? So, and it is an interesting story because in the book of Professor Khalil, in chapter 14, there are two different chapters. One called sliding mode design and the other called Lyapunov redesign. And my goal today is to say you the following. Okay, guys. Suppose that you have your task, you're perfect in your task. You know something about your stability of your controller. So, and my question is, how and what we are able to add something new, some new injection from modern sliding mode controller in order to have desired behavior of the system. You thought about it, even there are some perturbations. Okay? That's a main goal for me for today. And so, let us return to this classical name, Lyapunov redesign. And the classical joke about that is, would you like to change Lyapunov? No, I would like to change Lyapunov function. That's the difference. Okay? So, this is a group of people which made this theory, classical part of theory, in end of 70s, early 80s. This is Professor George Lakeman. All of them, minus the Ross Barnish, are his students. All of them are retired, and this guy unfortunately died. But that's more or less, that is why it's for sure classical topic. What they've done? They are telling, okay, guys, what you have? We are trying to solve some optimal problem. And solving some optimal problem, we have what? We have nominal system, because to solve optimal problem, you need to know all about the system. So that is why you already solved your problem, and you have nominal control for the problem, for the system you know perfectly. And also for such a control, you have Lyapunov function having standard properties, which are standard that the Lyapunov function is that the Lyapunov function is positive definite and its derivative is negative definite, and alpha 1, alpha 2, alpha 3 are standard growing function, means K class function. Okay? So what you are doing there? You are telling, okay, the life is not so beautiful. Why? Because in reality, we have uncertainties in perturbations. So that is why we suppose that we have perturbations in the input channel and also external perturbations. But in this case, all of them belongs in the span of the input vector. So this means that all of them, they are matched. And for sure, if they are perturbations, they cannot be bigger than the known part. So does it mean that this means that delta B should have some upper bound, and also perturbations should be bounded by some known function. So what will happen? Let's see what happens and what has been changed when we are searching for derivative of Laplace. What happens here? You see, we have found the derivative of the function. And what we will have? We will have this term which can be changed the negative definiteness of the derivative of our Laplace function. So that is why what we have to do, we have to do the following. We need, and that's the style in which the team of Professor Leitman was thinking. They were telling, okay, guys, what we need? We need to ensure that this story can be neglected. So, for this story to be neglected, what do we need? We need that this WT, which is no more than product of D by derivative, spatial derivative, means by space variable, of Laplace function. This story will be negative. So what does it mean? This means that the sign of this should be negative with respect to the sign of that. So what they've done, they told, okay, guys, if it will be so, okay. This means that the sign of this should be opposite than the sign of omega. So what they told, we need somehow to put as a new control something which is negative, which is opposite of sign of W. So, and they offer the story called unit control. Why it's unit? You see, the norm of this control, this part of the control is unit. So, in the scalar case, it is no more than omega by sine of, by model of omega, it is a sine. In the vector case, if we will multiply this by W, we will have W square, norm of W squared divided by W. So we will have precisely norm of W. So what happens? We will factorize W, and then we will see what happens here. This bracket should have negative sign. How it's possible? Because you see, this bracket should be positive because we have minus here. And this means that we can factorize by norm of W, and we have such a bracket, and such a bracket should be negative, and that's the condition for a design, as they told. Okay, if this is negative, so clean up the hand and tell, okay, if it is negative, we don't need to consider it, and we are finishing here telling, oh, under such a condition, using such a control, what we are able to tell. We are able to tell the following. We are able to tell that after such trick, what happens? We can neglect this part, and we can tell that initial Lyapunov function, nominal, will be also Lyapunov function for which system? For that's the key point. To have Lyapunov function the same, even the system is perturbed. Why? Because I've used such a control. Good. Perfect. So that is why what they told. Okay. Finally, you see, this is a key picture for me to start to think about this work, because here is Professor Leitman, here is Professor Corvette. I feel a little bit more young. It was 94, and this is my teacher, Professor. So, and why I've started to think about that? Because, you know, the good things should return. You should return. And that's what we've done recently in the paper. More or less recent, 2024, from the end of 2024. It is regular paper and transactions. So what we've done the following. We are taking into account all of recent type of controllers allowing you to do the same. But to do that, what it was necessary? To see a redesign from the view of person which deals with sliding. So, and that's what I will tell you. So, the same story from the other side. Okay? So, what's the same story in the other? What we are telling? Okay, we return to the same condition, and what we will see? The viewpoint of Leitman and Kim was okay to make all our best to put this term negative. Okay, but if you will see it from the view of sliding mode control, you will see 100% different story. Why? What is the difference? The difference is that they are putting here something like discontinuous control, and they are telling about sign of this term, and they are telling, okay, after that we can neglect it. But sorry, ma'am, sorry. What happens if you are putting negative, if you are putting relay control? For sure you will have sliding. So the sliding mode vision of the same story is 100% different. Why? Because what we don't need to think too much about this. What we need is just nullify this. If we will nullify this, for sure we can regret it. So that is why what we are doing here is trying to put our understanding of redesign. What does it mean, our understanding? To ensure the existence of sliding such that after a finite time, your Lyapunov function will be the same. That's the difference. So, because people, it's a group of Leitman, what they've told, okay, it is negative. What we are telling, it is the other story. It will be zero. That's the difference. That's the key. So that is why we've tried to see the same story from the other eyes. So the first glance is the following. Okay, let's see this W like a sliding surface. If we will see it like a sliding surface, so in finite time we will arrive there. And that was a key point for us to start. We are telling, okay, let's consider W like a sliding surface. What happens? Of course, it is normal supposition about Laplace function derivative. It should be of relatively one. So what happens here? What happens here is the following. If we have W as a sliding surface, what we need, we need to split the space, the original space, into parts. W and W are two. So what we need to show that W will be reachable in finite time. What happens here? If we will be already on W, we should suppose that the system has some so-called ISS property in the time of reaching field. That's what we should suppose, and we will do it. And so, if it is so, and it is more or less reasonable, what will happen? We will see W dot, like this one, and we should design a controller such as it allows us to reach W in zero in finite time. What's new here if we are dealing with sliding mode? In sliding mode controls, the first step of design is to neglect what you know in the system. You can compensate what you already know. It calls nominal equivalent control. Equivalent control is something which allows you to slide. Nominal equivalent control, it is not that. It is something you know about system, because if you will compensate it, you will have an option to deal just with uncertainty. Because what you know, you are able to compensate. What you don't know, you are. And that is the field of battle for sliding. That is why, what is the first difference between the approaches? Fridman team did not see the story about possibility to compensate known part. That is why they made the gains bigger. So, and if they use discontinuous controller like a unit control, they should make bigger the gain, and it results in the bigger charter. So that is why. What happens here? First of all, we've done the first step, we've compensated the known part. And so what happens? Then we can use the same unit control, and we can have a little bit better result. Why? Because we already compensated, we know. That is why we will be able to ensure sliding mode. So we will be able to ensure W equal to 0 with less efforts. And that's very good. So, and this is the condition, let's say, it is more or less similar story, but the conditions are very much more simple because already compensated a nominal part of. Then, what happens? Why unit control is not so good, or could be not so good in the case of fault-tolerant control? What's the problem here? In the fault-tolerant control, you need to work in such a manner that if one channel will be failed, then another channel will be not failed. So if you use unit controller, what you are doing. You are telling me that my controller, how it works. It works like W divided by normal W. If just one coordinate will not go to zero, all of control will not go. So is it good for? For sure it is not good for total. That is why we should consider another option. What is another option? Maybe not work with the gun because with the canyon, because unit control works for all of the cycle. So it is like to shoot with the canyon, yeah? because you are working in the cycle. So the other story is to deal with channels with a pistol. In which sense? One by one. Okay? To do that, you can use the other story, which is simple relay control. Channel by channel. If you will do, you will be able to say, okay, maybe one channel will fail, but the other will still work. That's the key point. So, and that is why here it is the first step. The first step is telling, okay, if it is so, what will happen? We will have advantages of unit controller, which is what? That all the discontinuities only is in a region. So that is why all components will converge at the same time, and the gain should compensate, mathematically speaking, two norm of the perturbations. So disadvantages is that if one channel will fail, all will. And the other story is democracy maybe is good, but the problem is that in some channels the signals are weak, in some channels the signals are strong. So why we need to use for some channels when the signals are weak all of the game? It is not business. So maybe we will kill the problems one by one. So that is why the games are individual. And when you will realize in the future such a controller, what you will have? You will have the problem that W divided W divided by normal W. What does it mean? This means that near to zero, your computer will fail. Why? Because you need to divide by zero. So what is simply to realize? Really or this story? For sure. Really you cannot do nothing because with any value of your function, really will be uniquely defined. The computer will not stop. Okay? So you will not lose the precision. So, and that's precisely the first approach to the things. You simulated a model of 747, even some toolbox, and what happens? Classical unit control uses personal G, but you are not safe for all the channels. If you are dealing with channel individually, nevertheless, you need to use a little bit more energy, and that's what. But what is the yellow line? The yellow line, if we are using unit control, and the similar will be this relay, you will use much less energy because you are able to compensate known part of the. That's number one, let's say, advantage to see the story from the viewpoint of sliding. So now I have to introduce the second story. Second story, what is modern sliding? Modern sliding mode control is a result of the fight with the chattering. So what we are doing, we are trying to substitute this continuous control with continuous. That's the main goal. So, and that was a first attempt to do it. It is precisely the papers when I've shown when it is reasonable to substitute this continuous controller with continuous one, which still gives you a finite and convergence, and also even convergence for the first derivative. So you see, this is a standard relay controller, and here is so-called super twisting controller, because when we designed it, Professor Leonid was young, twisting. So it's called super twisting. So why? And you see, it is PI. You are telling me, guy, are you okay with your hand? Where is PI here? But here is PI in which sense? In such a sense that you see, here is continuous function proportional to position. Not proportional because it's proportional in the sense of the square root. What does it mean? It means that we have a function like that. It is parabolic function, but this parabolic function is still continuous. So that is why it will be continuous, but with one bad feature. Which is a bad feature? The bad feature is that it will have here is a. Why? Because the derivative of square root so near to zero, you will have infinite gain. So that is why it is still not Lipschitz. And for sure you will chatter a little bit, but not so much. That's what I will speak. So it will give you even better control, and you can find here a condition how it works. How you can adjust it. We need to adjust that even one constant, taking into account that initially you have two. So why? Because constant K2 is a what? Is constant of integrator. You see? Why? Because we need to integrate. So that is why what you are asking for this K2. K2 should cover not perturbations, but derivative of your perturbation, because it is in the second line you to see what you are able to compensate, you need to have perturbations. So that is why K dot should be adjusted, taking into account the derivative of your perturbation. And if you have it, you will automatically have T1. It is not a big deal. So that is why what we've analyzed is their behavior with respect to here, with respect to the first order, second order actuator. You see? Here. So what happens? You see here. In standard sliding mode, the chattering, the amplitude of chattering proportional to the filter time. Here, because it's second order sliding mode, is proportional to mu square. The frequency here is every time greater, the frequency here. So the frequency is less. And the precision with respect to energy here is of order 1 and here is of order 2. Let us see the same story in graphs. You see, the blue line is continuous. The red line is traditional relative. Here, what one can see, that if your actuators are fast enough, it is good to use continuous. But if you use, if you have your slow actuator, you need to have strong power and put really. So you see, I was living in my life in 2 countries, Russia and the US. And I know that in both of them, there is not too much democracy. And this is a reason to see what happens. If your state, your government, if your state is weak, and if you have a lot of corruption, so it's better to have real control. If your system is, your actuator is fast enough, not too much corruption, democracy is good because it's good. Okay? It is, let's say, it is just interpretation from my experience, but it is a law. So if you'd like to have a control in the system in which the actuators are slow, there is no other choice, really. Otherwise, if your actuators are fast enough, you can use democracy. Means continuous control. It is very, very strong law, but I think it is clear. And it is not because they are good or they are bad. It is like to control. And the same, but what is interesting, the frequency in continuous control is every 10 years. So in relay control, you need to act very fast, every time fast. Okay? So now, the same story is with energy. If your actuators are slow, you will lose less energy with relay because you will have another frequency to switch. Then this continues. That's very interesting story, but this is a key problem. Okay. The next story is about Lipschitz controller. Lipschitz controller is in reality also second order controller, but they are Lipschitz. Why we need Lipschitz? Because in the previous, I've already told you this story is good because it's continuous, but it's still what it still has infinite gain. Okay? So what people are telling, what they will do. We will consider the same story here, but what we will do? We will apply standard relay control with the linear surface, and we will apply the same story signal, but with this surface. Why it's good and why it's bad? The point is that this one, if you will see it from the viewpoint of second order system, you will reach first here, and then you will reach here in finite time. So looks much better, theoretically and practically also. But the point is that to do that, to generate such surface, you can through integrate, you need to know derivative. And that's very, very tricky story. Why? Because imagine that you know derivative. If you know control gain is not so interesting. Why? Because if you know derivative, you know perturbations. If your gain is unknown, so in this case it works, and you prove that you can do the differentiation control separately. That's another story. I would like to show you the results. The results are here. You can imagine here is a square, here is a cube. So, and the frequency is also every time less. But here, it's very interesting story. If you will do the first order sliding mode, you can put the surface very aggressive, because this term will be negative and it will cause instability. So here you see what happens. There are 3 lines now, and what was surprised even for me was I never thought of it. But what happens? You have here 3 algorithms to compare. So, and these 3 algorithms are the following. The red line is precisely liquid controller, ensuring finite time stability. But, and for sure, it has better properties than supertwisting, because supertwisting is continuous and the other one is Lipschitz. Perfect. The third one is also Lipschitz, but be careful when you choose a sliding surface, because what happens? If you lose the ball. So, main conclusion. Why you can do with sliding mode all of your life. At least you see me, I'm dealing with chattering property all of my life, and I'm still alive. Why? Because you see what happens. Working on chattering, I'm every time suppressing him. But I know that I will never win. So that is why I can work all of my life, making it better and better. And so I will have a job for all of my life. Okay? So it is like let's say my own story, but you see why? Because you can do we were able to make better and better, to make the amplitude less and less, to make an energy less and less, but we still have a lot of work. So why I'm telling you about that? Because finally, what I have to tell, I have to tell the following. Finally, what I do need, I do need to make a redesign based on that superfluous. Of course, it is generalized, as well like that. You see here, say one term which is looks like square root because it's W divided by square root of normal W. It is like square root in vectorial case. The same story here with the sign. So if you will need the details, I'll give them to you. And it is in our paper. So it is part of the proof. It is generalized for multidimensional case and story like that. But what is important here that we were able to make a redesign for both, for Lipschitz and for continuous. So I think that my time is near to be finished. That is why let's go to my final slide. First, it's the same story, it's the same model of B747, and you will see that's what we had. Initial with relay control, with unit control, and if we are using modern controller, you see how we diminish the energy of the controller we need to maintain for tolerance. So, and finally, returning back to your classical problem, what I bring you, okay, you have suites here. What is my suite? My suite is the following. You see, suppose that you already have your controller. What is my 20 cents per your dollar? So my 20 cents is that you are able to realize it in 5 different ways. And that's the list of the possible realization of the design. You can do it in 5 different ways. So, and here is restrictions of these ways. So, first of all, if the controllers are discontinuous, you can compensate bounded perturbations. Okay? So imagine that you have 2 policemen. The only you need is what? Is to know if the only you need is that they will beat and they will stronger than the victim. Otherwise, it doesn't work. Okay? But the victim cannot grow up. So now, what is a clever way to do it? The clever policemen, what they know first, what they are investigating first. When the girlfriend of the victim is leaving. So that is why, or when the mother, it doesn't matter. What's important? It is important that they will show, they will, let's see, predict the way, the direction in which victim will come, and will wait him there. So that's what does it mean, second order sliding. Second order sliding controller means that they are clever, and what they will do, that they will guarantee the convergence not only to the unknown, to the variable you'd like to slide, but also to its derivative. And that's the sense they will predict when the girlfriend of this victim is leaving, and they will wait for him then there, and so and they will keep him. So, and what happens? So that is why there is a second round here. Telling, okay, there is Lipschitz controller and continuous controller. What are the restrictions there? The restrictions there are that you see what happens, that in Lipschitz function, you can have also bounded, but you also can have unbounded growing together with time. So that is why, what happens here? Lipschitz and continuous controller are able to compensate first Lipschitz bounded, but also Lipschitz unbounded. Lipschitz which are growing like a linear function of time. And also, there is another restriction that if you will use Lipschitz controller, you need also to ask that they will be bounded in the state area. That's the restriction. So, what is the final slide? The final slide is no, semi-final. Semi-final is that you can see this approach. What is the main problem when you are doing sliding mode? How I will choose sliding surface? Because you know what, let's say, my professor, Professor Rupkin, was also born in Soviet Union. For him, it was important what the Communistic Party was doing. So he told, okay, we will do what Communistic Party is doing. We will take the surface, I don't know from where, but my soldiers are able that we will follow. Here is a little bit more democratic in which sense? That you have constitution, you have nominal behavior of your population. And what you need to, why you need to use policemen to treat the people which wouldn't like to follow. That's normal. And so that's what happens here. They will treat the site with such a controller only the perturbation. That is why what happens? Lyapunov function for nominal system generates you a constitution. That's important. And this constitution, it is simply to follow by policy. So the constitution should, I mean, sliding mode should be adequate to the people. And that's the point. If the people are good, so they will follow. And the only you need to use the policemen is for the people which are not following. So that is why your state will be much more stable and easy. And that's the key point. And finally, that's maybe a main story. What is the main story here? There is classical Lyapunov redesign. We have nominal function and we have unit function. Now, the situation is a little bit different. Why? Because as you perfectly know, Lyapunov function is not unique. I can be married with plenty of girls. I will sell every time. I will sell them every time that she is unique. But I know that there is a set. So, but what is important here? That Lyapunov function will generate you a surface. You will arrange with her the rule, and then you will follow. And that is why the nominal Lyapunov function, each one, generates the surface. Okay? And then you can use a lot of the methods developed by modern sliding controls to follow. And then there is one other story that all of the things which you are able to compensate, you will not compensate through policy. You just need to correct the control law, and that's all, without any change. Okay? Because chattering, if you'd like to compensate uncertainty, if you would like to compensate perturbations, you cannot avoid. But at least we need to make a little bit less the law. So my time is finished. I'm not sure if you are lucky, but you have sweets. So thank you for that. So I think that, fortunately, let's say, I would like to present you. So my students gifted for my birthday when I was 17 a picture in which they showed me like a person which was living in Mexico and bring to the pyramid, you know, and the next is popular pyramid. My, let's say, Bible, my car, or my constitution is sliding. So I gave them my constitution, and that is why we, a small group of professors, generated around 200 PhD in Mexico in around 50 years. And what has happened that, let's say, that's what I would like. I would like to bring also my laws, my sliding mode laws, my sliding mode idea also here. Maybe they will be useful and they will be fruitful here. And that was more or less what I came to. Thank you. And so, questions, please. If they are short, if they are not short, I will be tomorrow here and today till 4 also here. Please ask me the question, send me emails, and what is important story. I'm managing a seminar, official seminar of Technical Committee of IEEE Control System Society for Variable Structure and Sliding Mode System. It is every Wednesday, 9 p.m. here time. So all of you, which would like at least to see the Zoom seminar about that, you can send me an email. I will add you in the database, and you will see. Maybe it works for you, maybe not. Normally, I'm sending it Wednesday. You will, some of you will receive today an announcement of the next seminar, which will be February 4, and it will be about multi-agent systems and the modern version of sliding mode differentiator. And then for 11, it will be the this presentation will be from Rodrigo Aldana from University of Sevilla. Then it will be a presentation of people from Superlec France. They will speak about optimal division of sliding mode control. Then it will be Professor Avrajenko, also from France, but from Grenoble. He will present the precision of sliding differentiators approach. It is not precisely of sliding mode, but how to estimate the derivatives and which is maximum precision. And so it is what I have in my hand because printed seminars are already very planned. So each Wednesday you will have sliding mode showing some sense. Okay, so you are welcome. And please send me the letter. So if you don't like the talk, you cannot attend it. Nothing obligatory. But maybe it will be interesting for you. At least you will see the new approaches to this things maybe you know and you know how to. That's more or less. So now. Questions? Sorry to be so unclear, but you will have compensation. Thank you.
Thank you.
So I hope I didn't, there is a Russian joke telling that you know the first class, but never know the next. So let's think that it was the first class. And I hope that it will be nice. Thank you. Okay. Thank you very much. Thank you. That's what I do. No,
Please take the sweet coffee, tea, juice.